Alright, hello everyone. So we are going to learn a new theorem regarding convergent sequences. So the theorem is, it says convergent sequences are bounded. Okay? Alright, so what does it mean for a sequence to be bounded? Well, in simple words, take all the terms in the sequence, okay? Take all the terms, take the absolute value of all the terms. That means assume that all the terms in your sequence is positive, okay? And then you can find a constant where every term of this sequence is less than that constant. So in simple words, if you take the absolute value of every term in the sequence, so all these values are less than a particular real number. So that real number, let's say it's capital M. So bounded, right? Okay. Now don't get me wrong, this capital M doesn't need to be a term in the sequence itself, okay? It could be any real number as long as that real number is larger than every term in the sequence. I mean absolute value of every term in the sequence, okay? Alright, let's prove this. Now this only happens, not only happens. So the idea here is, for convergent sequence, you are guaranteed that your sequence is bounded. Okay, so you get the guarantee that it's bounded if you have a convergent sequence. Okay, all right. Now for a fact, we know we are working with convergent sequences, so we know we can use the definition of the convergence, right? So that means the definition is, for all epsilon greater than 0, there exists a capital N that belongs to the natural number system such that, so I'm writing the definition because we want it, such that any position that comes after that capital N position, for any position, likewise, it implies the difference between the term of the sequence and the limit is less than epsilon. So let's use this definition to show that our convergent sequence is bounded. So what do we want to show at first? So we want to show this inequality. So a sequence is bounded if you satisfy this inequality for all n, okay? So for all n here means for every term in the sequence, absolute value is less than a capital M, a certain real number. So that we want to find that capital M. We want to see how it looks like, okay? So that's the aim of this proof, purely to get this inequality, okay? All right, that's our goal. Well, now what I'm going to do here is, this epsilon is arbitrary, right? The choice of epsilon is arbitrary. I mean, we say for any epsilon. Let me change this by choosing a certain epsilon value. Let's choose our epsilon to be 1. I'll later tell you why, okay? All right, so for epsilon equal to 1, the definition stands like this. Perfect. Now here's something about this definition that you must understand. This is very crucial. Take a sequence, okay? Take a sequence that, let's say, it looks like this. Now here's the thing. This definition says, so let's take a position capital N, okay? So for epsilon equal to 1, every term that comes after this capital Nth position, that means all these terms, okay? So it's basically neglecting all the terms that comes before capital Nth position, okay? So they are neglecting these terms that are here, okay? Now this definition, in this definition, what I want to say is that in this definition, we only work with the tail of the sequence, okay? That's very crucial. That's very crucial. If we are only working with all the terms that comes after capital Nth position, okay? All right, I just wanted to clarify that. All right, just keep that in mind, okay? It will come to bite us. All right, now what I'm going to do is, I'm going to take this fact here. All right, so let's write this inequality. Now we can use the triangle inequality here. So there's a triangle inequality that we can say, if you have absolute value of A minus absolute value of B, this is less than or equal to absolute value of total absolute value of A minus B. So this is a standard inequality. If we use this inequality, capital A is like S sub n, capital B is like S. So we can say absolute value of Sn minus absolute value of S is less than absolute value of Sn minus S, which is less than 1, where 1 is epsilon. Okay, now we can drop this part and say, well, we can say of course absolute value of Sn minus absolute value of S is less than 1, right? If this happens, of course this happens, right? That's an obvious fact. Alright, now what we can do is, here's what's going on. Now what we can say based on this last result, let me write it again, because you know I'm a little bit messy. Let's take this S to the right hand side of the inequality. So it becomes addition, so it's absolute value of S plus 1. Alright, here we go. Wait a sec. Now this inequality looks like exactly what I want, right? Or in simple words, I can say, can I take my capital M to be absolute value of S plus 1? What do you think? Alright, okay. So what do you think? It seems to be like we achieved it, right? No, not yet. What's missing? What do you think? What's missing? I can agree with you. Yes, what we have here is almost looks like what we want, and someone can argue capital M is absolute value of S plus 1. But why it's not complete? Here's the problem. As I said you before, this definition, we use the definition of the convergence to obtain this inequality. But the n values that we are talking about is not for all n. Remember, they are not for any term of the sequence. They are for the tail. Remember, we have this term in the definition. This term says for any simple n terms that comes after capital N, this inequality holds. So this particular inequality, absolute value of Sn less than absolute value of S plus 1, holds only for the terms in the tail of the sequence. Okay, that's a problem. Then that does not mean, so well, what it means is that every term that comes after capital M n is definitely less than absolute value of S plus 1. So let's try to rephrase that. So we have this sequence. Okay, I'm trying to explain it to you using pictures. Okay, so this is the capital nth position. So what this inequality means is all the terms that are here are definitely less than absolute value of S plus 1. So only the tail is bounded by a absolute value of S plus 1. How about others? Here's what we can do. Here's what we can do to complete this proof. Now think about 3 scenarios. Okay, think about 3 types of sequences. Think about a sequence, a decrease in sequence, strictly decrease in sequence. That means terms of the sequence are decreasing when you keep on writing. Okay. Now from what we have so far, we can say that every term that comes after capital N is definitely less than absolute value of S plus 1. But these terms, what is the largest of these terms? Terms that comes before capital N. Well, the largest term could be the very first term, right? Because this is a strictly decreasing sequence. So we have S1, absolute value of S1, okay, which is definitely greater than every term in the sequence, okay, every term in the sequence, and we just don't know which one is bigger from absolute value of S1 or absolute value of S plus 1. We don't know who is bigger, but for sure we know one of them. I mean, in either case, if S1 is bigger than absolute value of S plus 1, then every term of the sequence is smaller than the first term of the sequence, right? Or if absolute value of S plus 1 is bigger than S1, that means not only it bounds the tail, it also bound every term that comes before capital Nth term. So what I'm going to say here is, just in case if you have a strictly decreasing sequence, I will choose my capital M to be maximum out of absolute value of S plus 1 and between absolute value of S1. So I will choose the maximum between these two. That if I have a strictly decreasing sequence, okay? But that's not guaranteed. I mean, if you have a strictly increasing sequence, think about this. If you have a strictly increasing sequence, okay, we know the tail, so this is like the capital Nth term. We know the tail is definitely less than absolute value of S plus 1, and for sure, because every term of the, so increasing sequence means terms are increasing, so any term that comes before capital N is definitely less than absolute value of s plus 1, right? Because the tail is larger than what comes before capital N. So here still for an strictly increasing sequence, this condition valid, right? I mean, you just take the maximum out of these two, right? So it works for strictly increasing sequence or strictly decreasing sequence. How about if you have an oscillating convergent sequence? I mean, having an oscillating sequence doesn't mean that the sequence is divergent. It could be convergent, right? How about if you have a sequence like it oscillates, it jumps between the values, something like this, but eventually it converges. So let's say the capital Nth term is like here, okay, and we know the tail is definitely bounded by absolute value of s plus 1, but it's just we don't know what's going on with every term comes before capital A. Well, we just don't know whether it's the first value largest or the second value largest or the capital Nth term is largest. We don't know. But one of them could be the largest. I mean, one of them could be larger than absolute value of s plus 1, or everyone could be smaller than absolute value of s plus 1. We just don't know. So what we do is, there could be a case where even though the sequence is convergent, that any of these terms that comes before the nth term, capital Nth term or the capital Nth term, could be the largest. Okay, so in that case we choose the maximum out of all of them. Then the proof complete. Now we can say for all n. All right, try to digest it. Okay, so let's try to summarize this. Now what it says here is basically the proof is that we use the definition, but the definition is only for the tail of the sequence, for every term that comes after capital Nth term. We know that the tail of the sequence is definitely bounded by absolute value of s plus 1. So we want to find m, like the maximum, not the maximum, I shouldn't say maximum, but a term larger than every term of the sequence, right? So it could be that this absolute value of s plus 1, or it could be any term that came before the capital Nth term, because any term that came before capital Nth term was not involved in this definition. So we have to add them. So we just take the maximum of every one of them. So maximum of all of these will definitely bound the term of the sequence for all n, for any term of the sequence, not just for the tail. So that's the idea. Okay, now I promised you I will explain why we need to choose epsilon to be 1. Well, here's the thing. You can choose epsilon to be 10,000, but think about this. Think about this. Think about the sequence 1 over n. Okay, we know if you write the terms of the sequence, the first term is 1, the terms of the sequence are decreasing, and we know the limit is 0, right? Oops, that's wrong. Limit, okay, limit is 0. So of course this sequence is bounded, and you can see it's bounded by 1, or you can see it's bounded by 2. That's also correct. Every term of the sequence is less than 2 or 3 or 4 or 1000, right? But we want the most accurate. The most accurate will be every term of the sequence is less than or equal to 1. So 1 is a good bound, right? Accurate bound. So that's what we want. You could have chosen 10,000 for epsilon. It would still work. Absolute value of s plus 10 would be larger, much larger, but we want an accurate proof, okay, a good proof. That is why we choose epsilon to be 1, and epsilon is an arbitrary number. Okay, all right. Now the final thing that I want to address is that again the theorem says convergent sequences are bounded. Now we were able to construct this proof based on the fact that the sequence is convergent. Okay, all right. Now how about the other way around? How about if you have a bounded sequence, does that mean your sequence is convergent? Think about this. What do you think? Pause the video. Excuse me. Oh, that's bad. Pause the video and think whether it's true or not. Let's say you have a bounded sequence. Do you want to know whether it's convergent or not? I mean, bounded mean like every term of the sequence is less than a number capital M. So it's sort of comfortable to say that sequence is convergent, right? No, but it's not true. Let me show you an example. Look at this example sequence, okay? Okay, I hope that you can see it clearly. Cosine pi n. Cosine pi n. Cosine pi n sequence. All right. Now this sequence is bounded because if you take the terms of the sequence, it's oscillating. It's oscillating between 1 and -1. So of course it's bounded, right? You are talking about the absolute value of the terms of the sequence. So every term is 1 if you take the absolute value. So the terms of the sequence are definitely less than or equal to 1 or 2 for sure. So it's bounded. But is it convergent? No, it's oscillating. It's neither approaching to 1 or -1. So it's divergent. A sequence bounded doesn't mean that it's convergent. Okay, not necessarily. Okay, but for sure convergent sequences are bounded, but you cannot say it other way around. So yeah, that's the discussion of this theorem. Hopefully it makes sense to you. Thank you very much. Bye bye.